Dear channel followers, my name is Wendasan Worku. In our last lesson, we learned thoroughly about rational numbers, including examples. Today, we will be learning about irrational numbers. As I told you before, my name is Wendasan Worku. If you are new to the channel, please become a family by subscribing and don't forget to like, share, and comment. Now, let us go to the lesson. Definition of irrational numbers. Irrational numbers are real numbers that cannot be expressed as a ratio or fraction of two integers, where the denominator is not zero. In other words, an irrational numbers cannot be written in the form of p over q, where p and q are integers and q is different from zero. This is the key difference from rational numbers. Rationals have exact fractional representations, while irrationals do not. When expressed as decimals, irrational numbers have non-terminating and non-repeating decimal exponentials. They go on forever without any repeating patterns. The set of irrational numbers is often denoted as part of the real numbers or capital R, but excluding the rational numbers or capital Q. Together, rational and irrationals make up all real numbers. Irrational numbers are uncountably infinite or far more numerous than rationals, and they are dense on the number line, just like rationals. Between any two reals, or rational or irrational, there is always another irrational. Properties of irrational numbers. Irrational numbers share many properties with real numbers, but have unique characteristics that distinguish them from rationals. The first property is non-terminating, non-repeating decimals. Their decimal form continues infinitely without repeating blocks. For example, a square root of 2 is equals to 1.4142135623 never cycles. The second property, closure or partial properties. The sum, difference, or product of two irrationals can be rational or irrational. For example, a square root of 2 plus negative square root of 2 is equals to 0, which is rational number. A square root of 2 times a square root of 2 is equals to positive 2, which is rational number. But a square root of 2 plus a square root of 3 is irrational number. The quotient of two irrationals can also be rational or irrational. The third property, no additive or multiplicative inverses that are always irrational. The additive inverse of an irrational is also irrational. For example, negative square root of 2. The multiplicative inverses or reciprocal of a non-zero irrational is also irrational. The fourth property, density. Irrationals are dense on the real line between any two real numbers. There are infinitely many irrationals and rationals. The fifth property, uncountability. There are uncountably many irrationals, or proven by Cantor's diagonal arguments, unlike the countable rationals. The last or the sixth property, algebraic versus transcendental. Some irrationals are algebraic, or roots of polynomials with integer coefficients, like square root of 2, while others are transcendental, or not algebraic like phi and e. These properties highlight why irrationals fill the gaps in the number line left by rationals. Representation and types. Irrational numbers appear in various forms. Square roots of non-perfect squares. For example, a square root of 2, a square root of 3, a square root of 5, a square root of 7, etc. Cube roots and higher roots. Cube root of 2, a square root of 4 times 3, etc. Constants from geometry. Phi, ratio of circumference to diameter. A, base of natural logarithms. Golden ratio, which is 1 plus a square root of 5, which is divided by 2, which is equals to 1.6180339887. Continue. Appears in arts, nature, and mathematics. They cannot be plotted exactly on a number line using finite steps or only approximated, but geometric constructions allow precise locations. For example, using a compass for a square root of 2. Operations on irrational numbers. Operations follow real number rules, but results may surprise. Addition or subtraction. A square root of 2 plus square root of 2, which is equals to 2 times square root of 2, which is irrational numbers. A square root of 2 plus in the bracket 1 minus square root of 2, which is equals to positive 1, which is rational number. Multiplication, a square root of 2 times a square root of 8, which is a square root of 16, which is equals to positive 4, which is rational number. A square root of 2 times a square root of 3, which is equals to a square root of 6, which is irrational number. Division, a square root of 8 divided by a square root of 2, which is equals to a square root of 4, which is equals to, or the result is positive 2, which is rational number. Phi divided by a square root of 2, which is irrational number. Irrationals demonstrate that the reals form a complete ordered field. Comparison with rational numbers. Rationals, finite or repeating decimals, exact fractions, countable. Irrational, infinite, non-repeating decimals, no exact fractions, uncountable. On the number line, rationals are dots. You can hit exactly with fractions, but removing them leaves irrationals, feeling almost everything visually. The line looks the same without rationals. Here are 5 clear examples showing different aspects of irrational numbers. The first example, a square root of 2, which is approximately 1.4142, continues infinitely. The diagonal of a unit square or side 1 has length square root of 2, proven irrational by contradiction. Assume a square root of 2 is equals to p over q in lowest terms. Leads to contradiction that p and q share factors. Geometric proof uses a right triangle. The second example, phi, which is approximately 3.1415, continues infinitely. The ratio of a circle circumferences to its diameter never repeats, never ends. Appear in circles, waves, and physics. Golden ratio, which is approximately 1.6180, continues infinitely, defined as 1 plus a square root of 5, which is divided by 2, appear in pentagons. Art, for example, Mona Lisa. Nature, for example, shells, plants, galaxies. Its continued fractions is the most irrational in approximation quality. The fourth example, A, which is approximately 2.718, continues infinitely, base of natural logarithms and exponential growth, appear in compound interest, population models, and calculus, transcendental and irrational. The last example, a square root of 3, which is approximately 1.73 continues infinitely. Height of an equilateral triangle with side 2 or diagonal in certain rectangles. Non-repeating decimals. Algebraic irrational. Visualized via spiral constructions on number line. Irrational numbers are essential in geometry, physics, engineering, and nature. They capture the continuous, precise aspects of the real world that fractions alone cannot express.